Electrochemical or redox reactions are incredibly useful, and that's because they're all about the transfer of electrons. One of the most important ways we use this is in what's called an electrochemical cell. You see, if we can get electrons to transfer from one substance to another substance and actually force those electrons to travel through a circuit or a wire or a light bulb, what we've really done is created electricity. Electricity is just the flow of electrons through a material, and so if we can get the electrons to flow using a chemical reaction, we can actually produce electricity with a chemical reaction. This you probably think of as a battery, but is actually called an electrochemical cell. A battery is actually multiple electrochemical cells all connected together. Each of those electrochemical cells is able to produce voltage and output energy that we can use to do all sorts of different things. To help us understand this, I wanted to work through an example so we could understand them a little bit better. So this is the example that we're going to work through. We're going to look at how an electrochemical reaction between aluminum and lead is going to create an electrochemical cell. So the first thing we need to do is figure out the half reactions involved, figure out which is going to be oxidized and which is going to be reduced, and then determine the voltage. Once we've determined the voltage, we are actually going to draw an entire setup of how this electrochemical cell would work. So we have two different reactions. We have an aluminum reaction and a lead reaction. And we don't necessarily know right away which of these is going to be oxidized and which is going to be reduced. What we need to do in order to determine that is take a look at a list of standard reduction potentials. So the list of standard reduction potentials is just a tabled value. If you don't have one, you can probably find one in a textbook, or you can just look one up and be able to use it. What we're looking for on this list are two reactions. One that involves lead turning into lead 2 plus, and one that involves aluminum 3 plus and aluminum solid. Since this is a standard reduction potential, they're all written as reduction reactions, and also the higher something is listed on the list, the greater the ability for it to be reduced. What that means is that in our two reactions, because lead is higher than aluminum on that list, lead is going to be reduced and aluminum is going to be oxidized. So what we want to do very first is actually write out these equations so that we can figure out what's going on. So we are going to write out our lead reaction very first. We know that it's being reduced. Anything that's being reduced is going to gain electrons. So what that means is I'm going to start with my positive ion. It's going to gain 2 electrons, and that's going to turn into Pb as a solid. The other thing we should write down here is the actual voltage. The voltage from that chart was negative 0.13 volts. And so that is the voltage for this reaction, and this is the actual half reaction. Going back to that list, we can find aluminum. Aluminum is right here. And since it's lower, it's going to be oxidized, but you'll notice it's written as a reduction reaction where it gains electrons. So what we're going to need to do is actually flip this reaction, and when we do that, we're going to flip the sign as well. So we're going to take aluminum, instead of it having it gain electrons, it's actually going to lose electrons. So we're going to start with Al. It's going to turn into Al3 plus and 3 electrons. This was our oxidation reaction. Make sure it's losing electrons, so they're a product. Make sure your reduction reaction is gaining electrons, so they're a reactant. Now, the potential for this one was negative 1.66, but because we flipped it, it's going to become positive 1.66 volts. And so that is the actual potential for this reaction. If we wanted to figure out the overall voltage, first, let's take a look at the actual reaction. You'd want to add them together so that you get equal numbers of electrons in both reactions. Since one reaction has 3 electrons, whereas the lead reaction has 2, the lowest common multiple is 6. So we're going to multiply the lead reaction by 3, the aluminum reaction by 2. And keep in mind, I did not actually include the potentials in that. The potential isn't about how many electrons move, it's about how badly that substance wants to lose or gain electrons. And that doesn't change whether it's 3 or 6 electrons that are moving. So what we're going to have in one equation is 2Al producing 2Al3 plus 6 electrons, whereas our other equation is going to have 3Pb2 plus 6 electrons, producing 3Pb. In that, our electrons cancel, and the actual reaction here is going to be 3Pb2 plus gaining electrons from aluminum, the aluminum becoming Al3 plus, and the lead becoming a solid. If we wanted to find the actual voltage for this reaction, remember the voltage of the cell is the voltage of reduction added to the voltage of oxidation. And so for our electrochemical cell, we're taking negative 0.13 volts. We're going to add that to positive 1.66 volts. So the voltage of this cell is going to be positive 1.53 volts. So essentially we have a spontaneous reaction taking place, and this spontaneous reaction is going to have lead ions react with solid aluminum to produce aluminum 3 plus and lead. Now, if we were just to put this all in one container, if we were to say, take a beaker, put in a stick of aluminum solid, so like aluminum metal, and then create a solution that had lead ions in it, well, they would actually just react immediately. They would exchange their electrons, so the aluminum would give electrons away to the lead, and then it would make lead solid, and those electrons we can't actually use. So when we create an electrochemical cell, we actually need to separate our two half reactions. So what that means is I'm going to take my oxidation reaction. I'm going to set up basically a container so that I can have a half reaction inside of that container. So what do I need for this half reaction? Well, this half reaction has aluminum as a solid turning into aluminum 3 plus. That's going to be in solution, and it's going to give away 3 electrons. So what do I need? Well, I need a solid piece of aluminum. The other thing is I'm going to need what is called an electrolyte, something that can actually allow the flow of ions. And since I'm going to be adding positive ions, I essentially need negative ions to be able to balance those. So if I was to make this solution, essentially a good bet would be something like aluminum nitrate. The nitrate would help balance out positive aluminums that are going to flow into the solution over the course of the half reaction. And by making sure I have like aluminum or maybe some ion that doesn't react, I can make sure that I don't build up a precipitate in my half reaction container. The other thing I need is a container for my other half reaction. So I need another container set up, and in that other container, it needs to have lead ions. They're going to react with electrons, and that's going to produce solid lead. So I'm going to have lead ions in solution, and I'm going to have solid lead. So I need to have lead ions in solution, so I need another electrolyte. A really good bet here would be something like lead nitrate. By making sure it's a nitrate, it won't react. I need the actual lead ions floating around in the solution or it's not going to work. And I need a place for solid lead, so we might as well put a piece of solid lead in there. I mentioned a couple of terms here. The solutions themselves are called an electrolyte. So an electrolyte is a solution that allows charged substances to flow. So when they talk about like Gatorade is full of electrolytes, it's basically just full of salt. The other substance in here would be this, the lead and the aluminum. They are what we call electrodes. An electrode is a conductor that allows electricity to flow. Now, in an electrochemical cell, it's also important that those electrodes and electrolytes are able to react and have the correct substances for our half reactions. Now, remember, the other thing that's missing from my reaction here is the electrons. The electrons actually need to be able to transfer from one solution to the other. And to understand what's happening, I think we should take a look at what's going to take place as this reaction goes on. As this reaction goes on, solid pieces of aluminum are going to react and turn into aluminum 3 plus inside of this solution. So you're actually going to build up aluminums in this solution, but it needs to be able to lose electrons to do that. And where do those electrons go? Well, they go to the lead ions that are floating around in this solution. So what I'm going to do is connect the electrodes with a wire. By connecting the electrodes with a wire, I can allow the electrons to flow. Now, what you would do in your design of your substance or your electrochemical cell is this is the part that actually connects to whatever it is that you're trying to power. If you're trying to power, let's say like a light bulb, then the electrons will flow through, get to the light bulb and flow through, make it light up, and then travel to the other side of your electrochemical cell. If you're powering your phone instead of a light bulb, you put all the circuits of your phone in the way so that as the electrons flow, they have to travel through all the circuitry of your phone before getting to the other side of the battery. No matter what it is, this is basically where you put the actual thing that you want to power is in between the two. As the electrons continue to flow through, being lost by this substance so that they could be gained by another substance, then essentially what we're doing is allowing that actual flow of electrons, which is electricity. As the electrons flow in, they're going to travel through the electrode, and then the electrons are going to react with the lead ions in the solution. And what happens is as they gain those electrons, the lead ions are going to turn into solid lead. That is essentially the idea behind an electrochemical cell, but there's one important thing we're missing. When we balanced these reactions, we talked about how we don't just balance for atoms, we balance for charge. And if you think about the charges in each of these containers, they're not balanced anymore. What's happening is a neutral substance is turning into a positive substance. A positive substance is turning into a neutral substance over here. This container is becoming more and more positive. This container is becoming more and more negative. And unless we balance the charges, this reaction won't happen. So what we need to do is connect them together and create something that actually allows the flow of other charges. That is what we would refer to as a salt bridge. And a salt bridge is basically a tube or a container or like a semi-permeable thing that allows the flow of ions. Usually you would make your salt bridge out of substances that won't react when they go in any container. A really good example would be something like potassium nitrate. Potassium ions are positive, nitrate ions are negative. Neither of these react to create any precipitate, so they'd be a really good choice in an electrochemical cell as the salt bridge. What's going to happen is as this becomes more and more positive, the negative nitrates are going to flow into the solution. That is going to start balancing the positive charge. As the positives leave this solution and become solids with no charge, potassium ions can flow into the solution and balance out the charges as they're lost. This then creates your electrochemical cell. Your electrochemical cell is two half reactions that are separated, connecting the electrodes with a wire and powering whatever you want by putting them basically in the way of those two electrodes. You have to connect the electrolytes together using a salt bridge that allows the flow of ions to balance the charge. The other thing we need to do is think about what's called the cathode and the anode. In this case, we have oxidation happening over here. This is considered to be the anode. The anode is the site of oxidation. The cathode is the site of reduction. And so when you have reduction taking place, that is the site of the cathode. I remember it because anode has the O, so it is oxidation. In an electrochemical cell, the anode is is like the negative part of that battery. So the negative part of your battery is actually where the electrons flow out of. They flow back towards the positive part of your battery. And so they actually are gained back on this side. This is how we draw an electrochemical cell, how it works, and why it works. And so hopefully this helps you understand one of the applications of an electrochemical reaction. Thanks for watching.